Morning, guys. This is the second video from lesson 4.6 that I'm posting today. And again, I'm trying to break it down to keep those file sizes small. I know it runs a little bit slowly sometimes when you're downloading videos. So I apologize for that. And I will talk quickly, but you have the ability to pause, rewind. So that's why I'm not going to really poke my way through the lesson. So obviously you have these notes copied in your notebook already. So let's kind of just go ahead right to this first slide. And I just wanted to remind you, we kind of went over this in an earlier lesson, or at least some of this in an earlier lesson, but there are parts of an isosceles triangle, and we're referring to a general isosceles triangle, not the ones that are equilateral, but just a plain old isosceles triangle that is not equilateral. There are some parts that you should be aware of. The base is the side that is across from what we call the vertex angle. And the vertex angle is up here, so that these two things kind of always go together. Which is a little bit counterintuitive because the base angles, which are right here and here, and I'll actually mark those so that you can see those. I'm not sure why they're not marked in your diagram. But the base angles of an isosceles triangle are the ones that are across from the vertex. So we basically have these parts in an isosceles triangle. The congruent parts are the important parts, and they're the ones we call the legs. The non-congruent side we call the base. The angle that's across from the base we call the vertex angle. And the angles that are across from the legs, so notice this relationship, and the other angle across from the leg, they're called the base angles. So you just kind of have to study that and know that. But the important thing is that what makes base angles is that they are across the triangle from the legs. And it doesn't matter which way this triangle is flipped. So if I rotate this, the base angle, or excuse me, the base is not always on the bottom. Again, what kind of makes the base is it's the one across from the vertex angle and vice versa. Okay, so again, we'll kind of fly through. You have that stuff copied, and it's just things that you have to study. So we won't spend too much time. The first theorem is kind of a big one. Notice the if and only if. It is a biconditional statement. In our book, they state it as two theorems. I saved your writing and wrote it as one condition or one biconditional theorem. But basically, we have this situation where if we know a triangle is isosceles, then automatically those base angles, or the angles across from the congruent parts called the legs, they will also be congruent. But the converse is true as well. And that's what we didn't kind of point out on that last diagram. So I'll real quickly draw a sloppy triangle here. But if I know that, for example, these two angles are congruent, then that automatically tells me that the sides across from those two angles are congruent, and therefore the triangle is isosceles. So it does go in both directions. If I know the sides are congruent, that tells me the base angles are congruent. If I know the base angles, or two of the angles in a triangle, are congruent, that's automatically going to tell me that the triangle is isosceles because the sides across from those congruent angles are congruent. The other one is kind of a straightforward statement that we all kind of knew intuitively, but now it's official. And we'll give you both the original and the converse here. But if a triangle is equilateral, which means all the sides are congruent, that automatically implies that it's equiangular, which means all the angles are congruent. But the converse of that statement is true as well. If I know all the angles are congruent, then it will automatically tell me the sides are congruent. And it's important to note that that's true only for triangles. That generality of sides being congruent implying angles being congruent and vice versa does not extend to polygons with more than three sides. And we'll learn about that in chapter 6. Okay, so moving ahead, let's go to the next theorem here. There are shortcuts to the shortcuts. So we have those four shortcuts, SSS, SAS, ASA, and AAS, to prove that triangles are congruent. But we have some shortcuts that we can apply if we know that the triangles are right triangles to start. So, either they're marked in a diagram as such, or we're given in a given information that, triangle ABC is a right triangle with right angle B. Whatever the situation is, we know they're right triangles before we begin. When that's the case, we do not need to use those shortcuts SSS, SAS, ASA, and AAS. We can use four shortcuts to the shortcuts. The first one is called HL, or hypotenuse leg, and it's, as it implies, the hypotenuse of one congruent to the hypotenuse of the other, and one of the legs of one congruent to one of the legs of the other. And it actually doesn't matter which leg. It could be this leg or it could be this leg. So either one will work. In addition to hypotenuse leg, you have leg-leg congruence. So you don't need three pieces. Again, you only need two. And basically this one straightforwardly says if one leg of one right triangle is congruent to one leg of another right triangle, and a second leg of another right triangle is congruent to the second leg of another right triangle, those triangles are automatically congruent. And naturally, once triangles are congruent, we know all their corresponding parts are congruent by CP/CTC. So just moving ahead with these shortcuts, we have leg acute angle, and it's really important that we are looking at the acute angle. The right angle does not count here. But if I know these are right triangles to start, so I'll make sure I mark them as such, then I can go ahead and say, all right, well, if you have a leg of one right triangle congruent to a leg of another, and one of the acute triangle or acute angles of the first triangle is congruent to one of the acute angles of the second triangle, that's enough. We don't need a third piece. The triangles are congruent. And again, it doesn't matter which leg, and it doesn't matter which acute angle you use. Both will work in any combination. Last but not least, we have the hypotenuse acute angle theorem, which is the last shortcut to the shortcuts that work for right triangles. And this basically says if the hypotenuse of one is congruent to the hypotenuse of another, and one of the acute angles, and again, it doesn't matter which one, so it could be this one or it could be this one, but one of the acute angles of one right triangle is congruent to one of the acute angles of another right triangle. Those triangles are then congruent. So those are basically the new information, and it just gives us shorter ways and new ways to prove that triangles are congruent if we know they're right triangles to start. So with that being said, I'm going to end this video and start the next one on this particular slide we're looking at. But there's your homework assignment right there. Get an attempt on those for tomorrow, and pay particular attention to numbers 8 to 25. They're the ones that we really want to focus on before that test. And you can see I have a couple of problems and a few more on the next slide ready to go that we'll just kind of go over in the next video.